Pierre for putting together a great workshop. Yeah, it's been a lot of fun, and it's really a pleasure to be here, so thank you. OK, so today I'm supposed to talk about hyperbolic extensions, I think. All right, so. Which was kind of the last thing in the title of this mini course, and so I guess I'm taking a different approach than Jing. Jing gave us this really nice big picture view of mapping class groups and Teichmuller space and all the beautiful stuff that happens there. So one could say more things about out of n and outer space that I guess I'm not going to do. So instead, I'm just going to kind of look at this question and kind of try to present how some of the ideas that we've been discussing so far this week, like hyperbolicity and strongly contracting property and geometry of outer space and folding paths, all comes together to kind of try to understand one topic here. Okay, so this is the goal for the day. Let me just recap a little bit. So this is about extensions. Remember, by an extension, I mean something like this. I think I'm changing the names of my letters. OK, so this is a group extension. And and let's suppose that, so remember the kind of general question is about hyperbolic extensions here is you have some groups and you want to combine them in some way and maybe get something hyperbolic. So let's assume that K and G are hyperbolic and also infinite, otherwise kind of boring. OK, and the basic question again is when is E maybe a hyperbolic group? OK, so let's just set up a little bit of notation here. Let's let X be, let me call it S, be a finite generating set of E. And let's suppose that it contains a generating set of K. OK, so inside of E, I think of K as a normal subgroup of E, and I want to throw the generators of K into it. So now I have, this gives me like a word length on E. And of course, my generating set for E also projects to a generating set of G, because this is a surjective map. OK, so I just map them forward. Some of the things are in K, they all die. The things that don't die give me a generating set for G. So now I have kind of like compatible word lengths. I have a word length on E that kind of makes sense with the word length of G, and also a word length on K. OK? So what does this give me? A word length on G in particular, because I'm thinking of the projected generating set to G, so I have a word length there. And also a conjugacy length, which I'll write this way, on K. I mean, of course, there's a word length on K too, but I guess I care about the conjugacy length. OK, so that's, again, the conjugacy length of some element of a group is just the minimal word length of anything in its conjugacy class. OK, OK. So now I get kind of a bundle map of Cayley graphs. OK, so let me just call it the Cayley graph for K goes to the Cayley graph for E, which projects down onto the Cayley graph for G. Again, I'm suppressing the generating sets that we have all here. So you should think about this as kind of like a nice bundle. So in E, every generator of E either kind of projects onto a generator of G, or I think of it as a generator of K. So I think of the edges in the Cayley graph of E as either being horizontal, if they're like a generator for G, or vertical if they're a generator for K. So then the horizontal edges just project down to edges of G. And the fiber over any point is a copy of the Cayley graph for K. OK, so it's kind of a bundle of copies where the fibers are Cayley graphs of G, and I project down here. OK, you kind of see the picture? OK, right, so I have that. So I think of, so I think of Cayley graph for E as having vertical and horizontal edges in this way I was describing. And remember that the monodromy, so I get this monodromy homomorphism of the quotient group acting on the kernel. So remember how that works. I don't know if you thought about this at all, or I hope it makes sense to everybody. So again, if I have something in G, since this is a surjective map, I could choose a lift in E. I get some element there. And then I could conjugate this normal subgroup K, and that defines an automorphism of K because it's normal. Okay? And then the different choices I get by choosing different lifts of my element G all give me potentially different automorphisms, but they differ by inner automorphisms, so there's a well-defined outer automorphism. Okay? And it turns out you can check that this map is actually a group homomorphism. So I mean, if maybe do that as an exercise if you haven't thought about it before, that this actually makes sense and gives you a monodromy automorphism. So this yields to an action, if you will. That's just how I want to think about it. An action of G on, so again, automorphisms of K act on elements of K, but here I have outer automorphisms, so they act on conjugacy classes. We've used that before. Okay, so this gives me an action of G on the set of conjugacy classes of K. Okay. All right, so now let me describe a different combination theorem. So last time I mentioned this Besvina-Fein combination theorem. So I'm going to mention another kind of combination theorem that's similar but applies in a different context. So this is the, maybe you're supposed to say MJ or Mij, I don't know. Anyway, Mahan and Pranab Sardar proved this combination theorem, which says the following thing. So it's a very general theorem. I'm just going to state it in a special case of group extensions. Okay, they prove something kind of more general for what they call metric graph bundles. Yeah, so the setup is as over there. All right. So it says that the group E is hyperbolic, provided the flaring condition holds. OK, so what is the flaring condition? I'll just actually tell you what it is now. Right, so the condition says that there should exist some number lambda bigger than 1, so a multiplicative kind of exponential growth factor here, and some other number, natural number, say, such that for any non-trivial conjugacy class alpha in K, I'll just think of an element, but I really care about its conjugacy class, and geodesic, let me index it as follows. In G, so some geodesic in G, and I want its length to be kind of bigger than this m. So it's a long geodesic, so it's kind of like length 2m. Okay. So anytime I have a geodesic like that in there in a conjugacy class, what I can do is I have the conjugacy class. I can apply so the group acts on the conjugacy classes of K. So I can apply all the things in the group to alpha and see what happens. Okay. So I could look at in particular G0. And I think I want to use inverses for whatever reason. So I could look at the length of the conjugacy class when I apply G0 to alpha. Or I could look at the length when I apply the first guy in the geodesic to alpha. Or I could look at the length when I apply the last guy to alpha. Okay, using this action on the set of conjugacy classes. And the condition is that I want one of these things, so the minimum of these two things, I want it to be bigger than lambda times the middle. Okay, so along this geodesic, I kind of keep track of the length of my conjugacy class alpha. And this is saying that in the middle, it has some length. And as I go either to the left or the right, one of the ways has to get bigger. OK? Oh, do I want? I think I want maximum. I want maximum. Yeah, sorry. That makes more sense. Yeah, so one of them gets bigger, the maximum. Okay, so you could think that like here I have my geodesic. You think of this maybe as a geodesic in the Cayley graph of G. I guess, I mean, my picture is not so important, so I'm writing it where you can't see it. But you imagine like, OK, I have like over G0, I have in the fiber, I have kind of some length that measures the length of alpha there. And then I kind of go to the left or the right, and things have to get bigger. So here's at G0, and at Gn, it has to be bigger by a definite multiple. Okay, and it could either be like this, where I flare in both directions, or it could be that maybe you know, in the middle I have some length, and if I go to the left it gets smaller, but as I go to the right it gets bigger. Then that's the rule. Okay, so every time I go some definite distance in a geodesic direction in G, it's getting bigger. Okay, that's the condition. All right, anyway, so the theorem says that if you satisfy this flaring condition, then the group will be hyperbolic. Okay, and this is, I mean, like I didn't write down the flaring condition yesterday, but it's some similar thing in the context of graph of spaces. Okay. Okay, so there you go. That's very good. Maybe some remark here. So it turns out that, I mean, as we kind of saw yesterday, what is this saying? This is saying that, like, well, I have to have some sort of complicated action on a set of conjugacy classes. And in particular, my image, you know, of this monodromy, that's what's doing the action, has to be kind of big so that I can satisfy this condition. So since the outer automorphism group has to be big, that tells you something about K. So there's a theory of, like, called the JSJ theory of hyperbolic groups, which kind of lets you decompose hyperbolic groups in a certain way. And then from that decomposition, you can study what their outer automorphism group is. And basically, the output of that is if you want to have a hyperbolic group K, where out of K is complicated enough for this to happen, there are not that many choices. Okay? So if you have that, implies that if you assume K torsion-free, so if K has torsion, maybe more complicated things could happen, but you know, at least in this case where K is torsion-free, then if E is hyperbolic, you must have K a free product of surface groups and free groups. Okay, so if you want to kind of study hyperbolic extensions like this with, let's say, a torsion-free kernel, you kind of don't have a lot of options for K. And in particular, you should maybe be looking at surface groups and free groups. Okay, so this says if you, this question, hyperbolic extensions, is really something about this context of outer automorphism groups of free groups, sorry, of surface groups, which are mapping class groups, which is what we've been talking about, and outer automorphism groups of free groups, which is what we've been talking about in this course. Okay, so it's very relevant to this topic. Okay, so this is some other maybe source of motivation for studying mapping class groups and out of N. Okay. All right, so that's very nice. So now, all right, so that's just a general thing. So you know, maybe keep this in mind. I'm going to erase it at some point, and then we're going to use it at the end. Okay, so hope you remember. All right, so maybe now let's turn to, you know, does this ever actually happen? Are there examples, you know, of this in the real world? So kind of historically, the first example where this actually occurs was already mentioned earlier today. So suppose sigma is a closed surface. And if I take a homeomorphism of the surface, then I can build the mapping torus M sub f. So that's the mapping torus of f. That's, again, just take the surface, cross it with an interval, and I glue the two sides together by the homeomorphism. And if I do that, I get a 3-manifold. And this 3-manifold fibers over the circle, because I just kind of built it that way, where the fibers are copies of my surface. Okay, so if I do that, I can then, from this picture, get I have the long exact sequence of a fibration on fundamental groups, and that just picks out for me a short exact sequence of groups. In this case, that looks like this. Okay, so a group extension where the middle group is the fundamental group of the 3-manifold, and the kernel is the surface group, and the quotient is Z. Okay, so I have a group extension like this. So as we know, the fundamental group of a surface group is a nice hyperbolic group. Okay, it's quasi-symmetric to the hyperbolic plane, which we saw was hyperbolic. Z, nice hyperbolic group. So maybe, in the middle here is a candidate for a potential hyperbolic group extension. Okay, and the theorem of Thurston, amazing theorem, says that if F is Pseudo-Nosov, implies that this manifold, this 3-manifold, admits a hyperbolic structure. Or a hyperbolic, let me say, Riemannian metric, as Jing mentioned this morning. Okay, and if you think about it, just like this says that the fundamental group is quasi-symmetric to hyperbolic 3 space. So in particular, that implies it's a hyperbolic group. Okay, and then this in fact turns out to be, kind of an if and only if. That's not hard to see. Again, we mentioned some things like that before. Well, now we know the classification of mapping class group elements, okay, and which was discussed this morning. And Jing mentioned that, of course, the homeomorphism type of this manifold only depends on the mapping class of F. So I might as well just consider the mapping class of F. So it's either Pseudo-Nosov. If it's not Pseudo-Nosov, then it's either periodic or reducible. Okay, if it's periodic, then the fundamental group has a finite index subgroup that's just a product. So then it's not a hyperbolic group. Okay, or if it's reducible, that means that my element fixes some conjugacy class up to a power. Well, that exactly means that that's the situation we had before, where you had some element fixing a conjugacy class in the kernel group. So then you have a Z plus Z inside, and then it's not hyperbolic. So if it's not Pseudo-Nosov, or then it's finite order, or it's reducible, and then you wouldn't be hyperbolic. So in fact, the only way to get a hyperbolic thing is if it's Pseudo-Nosov. Okay, so that's nice. And this is, I guess maybe I should say, this is like story of these like fibered hyperbolic 3-manifolds is like the best thing. And I was thinking that maybe I would say something about them, but now I'm not going to. Oh, anyway, but there's like a lot of beautiful things one could say about this. So you should go read all the papers and everything. Yeah, that's awesome. Okay, but we're going to do something much more mundane and sad to the anyway. All right, so that's one example. Here's a second example. So this is not really, maybe historically this isn't the exact second example, but it's another one I want to mention. So, okay, so we know we're supposed to be looking at free groups and surface groups. So here's an example where the kernel is a surface group. What about an example where the kernel is a free group? Okay, so here let's take an element of out of n, and from that I can build a semi-direct product which is the following, just to remind you how semi-direct products work. So that's the group generated by Fn, and I throw in one extra letter, and then I declare that this extra letter conjugates elements of the free group according to what the automorphism does. Okay, it's an example of an HN9 extension that we learned about, earlier in the week. Okay, so and I guess, I don't know. When you write this down, like maybe you think you really, this element, like what is this element? I don't know, because I only have an outer automorphism class. So like really you should pick an automorphism of the fundamental group to write this down. But it turns out that the output group you get only depends on the outer automorphism class. You can like check that if I take two different automorphisms that differ by an inner automorphism, the resulting things are isomorphic to each other. So kind of doesn't matter. OK, anyway, so just like before, so here we took an element of the mapping class group. We built this 3-manifold, and we got its fundamental group. This is exactly the same thing, actually. We're taking an element of the out of Fn. You could think of that as being realized topologically as a map of a graph to itself. You could take the mapping torus of that graph map, and its fundamental group would be exactly this. Okay, so it's exactly parallel story. And so this thing really is an extension. So I have a short exact sequence like this. So this is a group extension, and you again might wonder, here I have a hyperbolic group, when is the group in the middle hyperbolic? And Peter Brinkman in 2000 wrote a paper that says that this is hyperbolic if and only if the element phi is atoroidal. Atoroidal means that no power fixes a conjugacy class. And I mean a non-trivial conjugacy class, because everything fixes the trivial conjugacy class. OK? All right, so that's the definition. And again, we kind of saw that this is a necessary condition, because if some power fixes a conjugacy class, then inside of here I'm finding a z plus z subgroup, so it couldn't be hyperbolic. So what this theorem says is really that turns out to be an if and only if condition. As long as you don't fix any conjugacy class, then in fact you do end up with a hyperbolic extension. OK, and maybe let me just mention that this uses the Besvina-Fein combination theorem and the theory of train tracks. Oops, we're out of room. OK, and in fact, there was an earlier, in the Besvina-Fein combination theorem, they actually give another example of this, where the automorphism is irreducible and also atoroidal. And so that was also known. And then Brinkman kind of got rid of the irreducible case. Basically, yeah, so Besvina and Fein, you already had this theorem about the train track theorem, that we discussed before, this algorithm that says if you're irreducible, you have a train track. And then using that train track, basically, they were able to show the flaring conditioning that you need. And from that to conclude this thing. And what Brinkman did is, well, in the case where you're not irreducible, there's this theory of relative train tracks that kind of comes up. And he was able to use that and to, again, establish the flaring condition that you need. OK, so that's how this came about. OK, great. And any questions? All right. And then let me just also say, so those are two examples, one example with a surface group extension and one example with a free group extension. There's now kind of a general theory due to many people, Farb, Mosher, Kent, and Leininger, and to Ursula Hamenstadt. And other people have worked on these things too. And this is, let me just say, kind of a general theory of hyperbolic extensions of surface groups. And this is what goes under the name of convex co-compact subgroups of the mapping class group of the surface. OK, so I mean, basically, Farb and Mosher introduced this idea of convex co-compact subgroups of mapping class groups, kind of by analogy of the theory of Kleinian groups. There's a theory of convex co-compact Kleinian groups, and sort of using this analogy of Teichmuller space with hyperbolic space and so on. Anyway, they gave this definition, and they showed that sometimes those give hyperbolic extensions of surface groups, and then Kent and Leininger and Hamenstadt basically showed it was if and only if, and gave kind of lots of nice results about these kinds of subgroups. OK, so there's a very nice story there that I'm, again, I guess not going to talk about. OK, because this is a mini course about out Fn. All right, good. All right. So yeah, so let's go to free group extensions. And I guess maybe I should say that, so there was this theory of convex co-compact subgroups, a mapping class group, and then that kind of motivated us to think about free group extension. So I guess what I'm going to present now is sort of a theory that's designed to kind of mimic this as much as possible by analogy. Right? So this is sort of the motivation. Anyway, so if I talked about that, then I would just be repeating myself to some extent. Okay, right. So I just want to tell this story. Okay, so free group extensions. So now I have, let's just look at this case. Okay, some extension of the free group. And the goal is to try to understand these things. And in particular, what we know from theorem over here, that if we want to understand when these are hyperbolic, we have to know when the flaring condition satisfies. Okay? And what I want to do is use the geometry of outer space to study this flaring condition. Okay? And in particular, I kind of want to give a sketch of how all these ideas fit together. Okay? Okay, that's the idea. All right, so to do that, I have to discuss folding paths. Okay, which I think we're well set up to do and to understand. So if you think back to the other class this morning, last couple days, Jing was telling us about Teichmuller space, Teichmuller geometry, and in particular about Teichmuller geodesics. And how did Teichmuller geodesics arise? There was some question of I have 2 points in Teichmuller space, and I have the distance between them, which I defined as some infimum of some class of maps or whatever. And then there was the question of like, oh, is the infimum realized? And Teichmuller's theorem says, yes, it is realized by some map. And moreover, that map gave you a geodesic between the place. So there was this like unique realization Teichmuller map, and from the Teichmuller map, Jing built a geodesic. Okay, so we've already done half the battle, if you kind of remember. So we talked about I have 2 points in outer space. I defined this notion of distance, and we said, is the infimum realized? And we said, yes, it is. You can always realize the distance by some optimal map which has some nice structure, with like a chain track structure on the tension graph. And now what I want to do is kind of a similar idea, is use that structure to build a path now between the points. Okay? So that's the idea of folding paths. Okay. Right, so I have 2 points, again, in outer space with, say, an optimal map between them, sigma from gamma to gamma prime, with a train track structure on the tension graph. Okay, this is was the output of some of our discussion earlier in the week. And let me assume that the tension graph is all of gamma. Okay, that's the situation where I want to do this kind of folding construction. And if not, I can fix it. So what I'm trying to do is build a path from gamma to gamma prime. Okay, so I might be at some point where there is no optimal map where the tension graph is everything. But I can always move towards gamma prime in the following kind of dumb way. So I know that the things in delta are the things that need to stretch the most. So if I want to go towards gamma prime, I could just start stretching them and making them bigger. And while I'm doing that, making the other thing smaller. So that's just moving in a simplex of lengths. And if I make the things in delta bigger and the other thing smaller, eventually, and I just keep the same map, well, the stretch constant on the other things is getting bigger, while the stretch constant on the things in delta is getting smaller as I move towards gamma. And eventually, some other edge is going to now pop into the tension graph. Okay? And I could just keep doing that and moving around until every edge is in the tension graph. Okay? So if not, what I'll do is I'll just describe, I just do that process I described. So if not, I move gamma to some new point called gamma naught by stretching the metric on delta and shrinking the other edges to maintain always volume equal to 1. Okay? And as I do that, the Lipschitz constant as I move, the Lipschitz constant goes down. So I'm like kind of moving closer. And then eventually I can arrange for everything to be in the tension graph. So I do that, and I do that until all edges are in the tension graph. Okay, question? Well, yeah, it turns out you are moving geodesically. How do you know? So it's very easy to know if you're doing a geodesic in outer space because like we know if I just do this procedure and I stretch some things, and then I want to know what's the distance to the place where I ended up, we know it's the supremum over the ratio of the lengths of all curves. That was this formula. So just ask yourself, well, what curve got stretched most? Well, the most anything good I've gotten stretched was how much I stretched this. And there are closed loops in there that got stretched that much. So that's the most anything could get stretched. Something did get stretched that much, so that's the distance. So you moved exactly sort of how much you stretched this thing. And you know that like that point you built is also on a geodesic. So here I am at gamma. I do some kind of stretch to get to gamma naught. And I know that that's on a geodesic now to gamma prime because like to get from here to here, all I need to do is stretch everything in a delta the right amount. I've already stretched it part of the way, and now I just have to do the rest of the way. So you can kind of think about how that works. But anyway, it turns out when you do this, you're moving towards here. And the distance from here to here exactly adds as this distance was that distance. OK, so this is called a rescaling path. OK, anyway, so after you do the rescaling, you can assume the tension graph is everything. And now that I have that, I want to fold. So I think we've hopefully all internalized this, that you have illegal turns, you don't like them, so you fold them. OK, so that's what we're going to do. All right, so so for t small, so I'm going to describe like sort of an infinitesimal permutation of gamma that's going to move it a little bit. OK, I'm just going to tell you the direction to go in. I'll deform gamma to a new graph gamma t by folding all illegal turns for length t. OK, so what do I mean by that? I have my graph. Maybe here's a vertex. And maybe in my graph, maybe this is a gate, and that's a gate. So here are two gates. Well, that's a gate, and then this is also its own gate. Remember, a gate is an equivalence class of things that all make illegal turns. OK, so what I'll do is I'll just take these things, and I'll just take a length t segment of them, and I'll identify it all. OK, and I get a new graph. So this is fold. And now it looks like this, where this here is length t. So I just fold length t. OK, and then there's a quotient map from this graph to this graph that's one Lipschitz. I didn't stretch anything. All I did was identify some things. OK, and then I always have to rescale for volume 1. And then I call that gamma t. OK, so here's gamma, and then I go to gamma t. OK, all right, so that's a way to deform. For small t, I can do that, and I get a new thing. OK, and anyway, so that's totally fine. And my optimal map descends to this quotient because I folded illegal turns. And illegal turns are things that got identified, so it descends. OK, so my optimal map descends to to now an optimal map from this new graph still to the same target gamma prime. Okay, and it comes with the illegal turn structure just stays the same. Like I still declare these all to be illegal turns and these to be illegal turns. So those are still illegal turns. And these things are not illegal turns because they weren't before. So this comes with the train track structure. And now, so I fold for a little bit for t, and I got to here, and then I could fold a little more, and I just keep folding. Okay, and like basically, like eventually, my illegal turn might crash into another vertex, and then I would like lose track of what happened, but then I would just find a new illegal turn and start folding. Okay, so I do that, and then I can continue to fold. Can continue. They'll say can then continue to fold. Great. And it turns out, this is not very obvious, I think, but you can just keep this process. You can always find some epsilon where you can fold, and then you fold a little bit, and then you stop, and then say, oh, there's another epsilon. I can fold for a little bit. And it turns out, if you keep doing it, you eventually get to gamma prime. Okay, you make it there. So that's a theorem. I think this is originally due to Tad White in his thesis, that this yields a path of graphs defined for t in some interval. And this is a path from gamma to gamma prime. So I actually get all the way to gamma prime by this process. Okay, and that's, again, not obvious. And after I do that, I may parameterize such that, and I'll assume that I've reparameterized so that this holds, such that this is a directed geodesic in outer space with respect to the Lipschitz metric. So by directed, I mean that the distance from gamma s to gamma t is always equal to t minus s for all s less than t. Okay, it's an asymmetric metric, so you have to be careful about the order, but I'm measuring the distance from the less times to the bigger times. Okay, so OK, great. So Anne maybe mentioned that this comes with a train track structure on gamma t at all times. Okay, so it's a path in outer space. It turns out to be a geodesic. So so here's a theorem that, like, in fact, outer space is a geodesic metric space, a directed geodesic metric space for any 2 points. I could first do this rescaling business until I get an optimal map where the tensor graph is everything, and then I can fold, and I'll get to the place I want it to go, and I'll have built a directed geodesic between the 2 points. Okay, and they're geodesics with this particular structure of a legal turn structure with at least 2 gates at every vertex at every time. Great. OK, and maybe let me just mention that just like we saw that for pseudo-Nosovs acting on Teichmuller space, they have this 2 fixed points at infinity, and there's a Teichmuller geodesic axis for them. So pseudo-Nosovs have an axis that's a geodesic axis that's invariant. If I use the train track theorem that we know about now, that if you have an irreducible automorphism, it has a train track. From that kind, if you go to that point in outer space and you give it the right metric and you fold, you can build a bi-infinite geodesic that's invariant under the automorphism. So a train track representative of an automorphism via this folding process gives you a bi-infinite folding axis for the action of this on outer space. Okay, so that's kind of nice. Great. OK, so that's the first ingredient I need to talk about folding paths. The second ingredient about outer space comes from not the geometry of outer space, but from the geometry of a related thing called the free factor complex. OK, so what is this? This is a simplicial graph, which I'll call fancy F. OK, and the vertices for me will be conjugacy classes of cyclic free factors. OK? So remember, free factor is something, A, where I can write A star B. And I just mean A where A is a cyclic group. So another way to think about that is just a basis element. OK, so a cyclic free factor is just determined by a basis element. Not every element of the free group gets to be in a basis. Some do, some don't. So I'm just looking at the conjugacy classes that define things that could be in the basis. Maybe let me say that this is not the usual definition. Usually people take all free factors. But just looking at the cyclic ones gives you a quasi-isometric thing. So I'm just going to do that because it's simpler. OK? But usually people would have the vertices be any conjugacy class of any free factor. OK. All right, so the edges. So I have an edge between two conjugacy classes of cyclic free factors if alpha and beta may be jointly part of a basis. So after conjugating one of them, I can extend that pair of elements to a basis. That's the condition to be an edge. OK? All right, good. And as I said, this is a different, slightly different definition, but it's something quasi-isometric to the usual free factor complex. OK, we have a Lipschitz projection. Oh, but maybe before I say that, in the analogy with mapping class groups, this is like playing the role of the curve complex, which we've heard some things about, the curve complex. There's kind of many competing analogs of the curve complex, and this is one of them. OK, there's other ones. But this is the one we're going to use. All right, so I have a Lipschitz projection, which I'll just call pi from outer space to the free factor complex. OK, so how does this go? If I'm standing in a point in outer space, I have a marked metric graph. So I can look at my graph at the shortest loops, or the shortest conjugacy classes that are shortest at that point, which if you think about it will be some embedded loop in the graph. OK, and I just pick the shortest loop. That's what I do. OK, and the shortest, if you think about it in a graph, a short loop always defines a basis element, because I could just contract everything down to a point and then a tree and so on. OK, so then that's totally fine. So I just send a graph to a shortest conjugacy class at that point, gamma. OK, and that's not a well-defined thing. There might be two conjugacy classes that have the same length, but they'll be like next neighbors to each other. So it's like a coarsely well-defined map. OK, and let me also just mention that it turns out this is Lipschitz. OK, so that's like a thing you can check. If I move my graph a little bit, I change the metric, the shortest thing can't change wildly. OK, so it's Lipschitz. Good. All right. All right, so why do we care about the free factor complex? Well, if you've been paying attention, you know that we, or at least me, care about things that are hyperbolic, and probably outer space isn't. But it turns out the free factor complex is. So that's very useful for us. OK, so here's a theorem. Espina and Fein says that this complex is hyperbolic. So it's delta hyperbolic for some delta. OK, and maybe if it wasn't clear, I mean, it's just a graph, and I'm giving it the path metric, like where edges have length 1. OK, so and it turns out it's connected. Maybe that's not obvious, but it is connected. So the distance between 2 points is the length of the shortest path. OK, so that's the metric space. It's a geodesic metric space. We know what hyperbolic means. OK, now this is kind of a hard theorem, but I want to give you the idea of it because we need it, sort of. OK, so I'm going to give a sketch. OK, so the sketch is to use folding paths. Okay, so let me think about a folding path. And I can do the following thing. For alpha, some conjugacy class. So now let me just write this. I mean a vertex of the free factor complex. So I just mean a cyclic free factor. Okay. So I can look at the core of the cyclic subgroup over the point gamma t, right? Gamma t is a point in outer space, so it's a graph with an identification of its fundamental group with the free group. I have a subgroup, and that gives me a core, like we learned about on the first day. Okay? That core is just going to look like a loop, because it's just a cyclic thing. Okay? But anyway, so I get that thing, and it looks something like this. You know, I'm going to draw it kind of funny like, and it maps over gamma t. And what I want to do is pull back a legal turn structure. So gamma t comes with an illegal turn structure. I have an equivalence classes on the directions at every vertex. Okay? And alpha, as it's going around gamma t, sometimes it's making legal turns and sometimes it's making illegal turns. So I'm just, whenever I take an illegal turn, I'm just lifting that up here and calling them illegal turns. So all this is some loop with like broken up into segments that are legal and then illegal turns and then a legal segment that an illegal turn. So it comes with this structure. OK, good. So this will be an illegal turn. So those are those things here. And then I have kind of legal subpath. OK, here's a fact. Any legal subpath of length at least 3 grows exponentially. And this is just something you calculate based on the definition of folding paths. You say that like, oh, what happens when I fold is I'm just identifying these legal turns together, and then everything grows. But like I'm identifying them at a rate where if there's a too much of a distance between them, this grows faster than they can eat in at the sides, and they can never cancel each other. So you can just calculate that the length of the legal things grows if they're long enough. If they're close together, the illegal things could nibble and get to each other. Okay? But if it's long, that can't happen. That's just a simple calculation from the definition that's like unenlightening. Okay, great. So that's one fact. Another fact is that as you fold, by fold, I mean, I guess, like you're moving forward and you're just seeing how the core changes as you move along. Okay? So as you fold, illegal turns they can disappear. So it could be that like an illegal turn, as I fold forward, eventually it just kind of vanishes and like stopped, like that illegal turn went somewhere else, but alpha is not taking that turn anymore or something. So it could disappear, or they could cancel with each other. Okay, or illegal turns can collide and combine. Okay, so if I have a short legal segment between 2 illegal turns, they can nibble at the sides enough and then get to each other and turn into one illegal turn. Okay, but what can happen is that the number of illegal turns can only go down. As you fold. Okay? And of course, that means if I go backwards, that means they can increase. As you go backwards, going backwards is what I call unfolding. So if I go backwards, that means you could get more illegal turns. Okay? Okay. Great. So now, let me tell you the definition that Vespina and Fain made. Let me define left gamma of alpha, my folding path, let me call this folding path gamma. So I also think of it this way. So gamma is the name of the path. Okay, so the left projection of my conjugacy class alpha to gamma, this is the infimum of times such that the core, oh, I didn't write, this is my notation for the core. So it's alpha restricted over, that's, I just mean that by the core, okay? Alpha bar, the core over that thing. So that the core has a legal segment of length greater than or equal to 3. Okay, so as I go forward, I mean, alpha has some number of illegal turns. If I go forward forever, eventually they stop decreasing, and then the legal things between them grow. And then I get a legal segment that's long. Okay, so so this is the first time I see a long legal segment. Right is the other side. That's the supremum of times where the core has a long illegal segment. Well, let me say a long subsegment, a long segment without a legal subsegment. Of length greater than or equal to 3. Okay, so right, so you call a segment illegal if it doesn't have a long legal subsegment. Okay, so like it's like a chunk going along where every like little legal bit I took was short, less than 3. Okay, and then if I have a bunch of shorter than 3 things together, I call that an illegal thing. And this is the supremum of times where you have a long thing. And I'm not defining what long means. It's some constant. Okay. And the idea is that as I fold, everything eventually becomes legal, and I pass this infimum. And as I unfold, I get more and more illegal stuff, more illegal turns, and I get more of these illegal segments. OK, so here's the proposition. If I project the, so I look at gamma as my folding path, and I can look at left, gamma of alpha, and I can look at right, gamma of alpha. And that's some subinterval of the domain of my folding path, and I could take gamma of that. So that's just the left and the right, everything in between. That's some part of my folding path, and I project it all to the free factor complex. And in the free factor complex, this always has uniformly bounded diameter. Okay, so for my conjugacy class, as I go to the left, it becomes more and more illegal. As I go to the right, it becomes more and more legal. This is sort of like the balance time when it's like on the verge of switching from illegal to legal. And it says that, well, that might be far apart in outer space. But when I project on the free factor complex, it's right next to each other. Okay, it happens. So it's like a well-defined thing. OK, what does this give me? That's like, seems like a crazy thing to do. Why would you do that? I don't know. But you did. And what does it give you? So now, I could get a family. What is the family? It's the family of these paths. Okay, so I look at all folding paths, and I look at their projections in the free factor complex. In the free factor complex. Okay, and they come with projections. What are these projections? Let me call it P from the free factor complex to, so for each one of these paths, I'm going to define a projection from the whole free factor complex to the path. What's the projection? It's just that. I just send a conjugacy class to the image of left. So I look at the folding path. I find its left thing for this conjugacy class. I project it down. Right would have given me the same thing. It's well defined because it's bounded distance. So this is some way to get a map from the whole free factor complex onto each one of these paths. OK? OK, so here is the upshot, is that these projections are uniformly strongly contracting. Okay, just like we saw before. If I take a ball, so I pick one of these paths, I take a ball, disjoint from it, they say that the whole image of the ball will have uniformly bounded diameter for a uniform bound on all families. Okay, so there's some one number d that works for everything. Okay, so that's like kind of like the situation we were talking about the other day, where I have geodesics in my space. If I knew all the geodesics in my space were d strongly contracting, my space would be hyperbolic. Here, what do I have? I have some family of paths with some weird projections that happen to be strongly contracting. Okay, it turns out that that's enough to run the argument that we talked about to get that you're hyperbolic. That's the proof. Okay, so there's that. And the other thing you need is that these paths are coarsely transitive, meaning between any 2 points in the free factor complex, I can find such a gadget, such a path. And these two ingredients, via kind of standard arguments of the flavor of we talked about the other day, imply that the free factor complex is hyperbolic. Okay, it's like the same kind of argument. And it turns out, so like it's kind of amazing. Like yesterday we said, like, oh, if you knew all geodesics were strongly contracting, then you could run this argument with the triangles. It turns out you don't need them to be geodesics. You just need them to be something paths. And with some maps like this, and then the result is that the paths had to be quasi-geodesics, and these projections have to be closest point projection coarsely. Okay, so that's like the usual argument. Any questions? Sure, it's like, of course, that's how it goes. Yeah. Anyway, so that's the deal. All right, but it gets a little better than that. Huh? Oh, well, yeah, it is infinite diameter. Maybe that's not obvious. They also prove that. But it gets kind of better from, if you read their paper, for gamma, any folding path. Now I can define another kind of projection. I'll call it, I just made up a letter L. So I could do this instead of in the free factor complex. I could do it in all of outer space by just sending a point H in here. Well, I could just first, how do I write it? Yeah. So I first project so this is some graph in outer space. So I project it to the free factor that picks out some conjugacy class. And then I can project that conjugacy class to the GDS. I can pick out its left time. Oof, left. Okay, so this is some other way to define a projection now from all of outer space to each folding path. And Besvina and Fain prove the following thing. That given some constants, Kc, there exists a constant d such that if, I mean, they really didn't phrase it this way, but they basically said that if the folding path like moves, basically the diameters, when I project things like a ball that's disjoint to the folding path, if I then project to the free factor complex as bounded diameter. So that implies that if I have a folding path, such that when I project it to the free factor complex is a Kc quasi-geodesic, then gamma is d strongly contracting in outer space. Okay, and that's, I guess, with respect to this funny projection L gamma that I defined before. Okay, so basically they said here's a condition. If you have a folding path that when I map down to the free factor complex, you get a quasi-geodesic, which basically you should think that it's moving at kind of a definite rate. Because the maps, I mean, outer space it's the geodesic, and the map to the free factor complex is Lipschitz. So you always get the upper bound on the quasi-geodesic condition. So this is saying if the lower bound satisfies, then in fact that path is strongly contracting in outer space itself, not just in the free factor complex, if you use this funny definition. Okay? All right. So now we're getting somewhere. So in work with Sam Taylor, we kind of souped this up a little bit to the following thing. given KC, there exists a D. New chunk. Ooh, yeah. Such that if I have gamma is any KC quasi-geodesic in outer space such that the projection to the free factor complex is also KC quasi-geodesic, then the closest point projection is D strongly contracting. OK, so what do we do? Basically, as Fein said, this result for folding paths, and we kind of push it up to any path at all. It doesn't even have to be a geodesic, just a quasi-geodesic that has this condition that when you project to the free factor complex, it's a quasi-geodesic. OK, so it applies to anything. And basically, you can do closest point projection instead of their funny left. So now you can forget about left. Left was confusing. No one likes it. OK, good. All right, so in fact, so it gives you that. So let me say, hence, gamma is Morse. We learned that the other day. Strongly contracting things are Morse. OK, there's like a subtlety here because the argument on the homework, if you did the homework, uses that it's a metric space. And outer space is not a metric space. It's asymmetric. So bad things can happen. OK, but it turns out that in this case it works. OK, right. Anyway, so it's Morse. And also, let me remark that it's an if and only if. So this is if and only if. So in fact, if you had, let's say, at least any geodesic in outer space that happens to be strongly contracting, then it satisfies this property that when you project the free factor complex, it's a quasi-geodesic. OK, so what is this saying? Like in the spirit of strongly contracting things being great and being evidence of hyperbolicity, this is like telling you exactly which geodesics in outer space have that property. They're the things that exactly when you map them to the free factor complex, you get quasi-geodesics. OK? OK. So now, what do we have? We have some hyperbolicity in outer space. We know it has some strongly contracting geodesics. And these are tied to the geometry of the free factor complex. OK, so that's the setup. And now we can go back to extensions. OK? So this is our question. Again, this is the thing I was really trying to talk about, is these extensions. And I want to understand when they're hyperbolic. And I need to understand this flaring condition. OK, that's the goal. And remember, the flaring condition is something about G acting complicatedly on the elements in the conjugacy classes. Well, we just built this nice thing out of the conjugacy classes in Fn called the free factor complex. So maybe we should study how G acts on the free factor complex. OK, so that's the idea. So let's make a definition. Say the extension, this extension over here, is convex co-compact if the orbit map, so G maps to out of Fn, and this acts on the free factor complex. I guess I didn't mention that, but it acts on the set of free factors, and it preserves when things are jointly part of a basis. So you get an action like that. OK, so this homomorphism builds an action for me of G on the free factor complex. And I want that to be a quasi-isometric embedding. OK, so that's going to be my measure of the group G acting kind of complicatedly on the conjugacy classes of F. OK, let me make another definition. Let's call it purely atoroidal if no infinite order element of G fixes a conjugacy class. You might say, I don't get it. Like, if I knew the orbit map into the free factor complex was a QI embedding, that means it doesn't act with any fixed points. So like, how could I be fixing a conjugacy class? But remember, not all the conjugacy class is going to be in the free factor complex. Okay, so there's other ones. Right? And somehow this condition, you could still satisfy this condition, and maybe you would fix some conjugacy classes that weren't basis elements. So like, you need this extra condition. We've seen that this is like, if you don't satisfy that, then you're definitely out of luck. OK. Oh, good. All right. So now here's the theorem. And this was with Sam Taylor. If your extension satisfies these conditions, then the group is hyperbolic. OK. So that kind of answers the question about when things are hyperbolic. Great. OK, good. So now, in the last 7 minutes, I want to prove the theorem. OK. We did most of the setup. Now we're in really good shape. OK. All right, so let's do the sketch. OK, because yeah, so everything's going to come together. I don't know. Maybe it will. Maybe it already did. Who knows? OK. So let's, as before, take a finite generating set of E. As before, that contains a basis of, maybe I'll call the basis B of the free group, and projects to S, a generating set of G. So as before, we get the conjugacy length with respect to our basis in F and the word length in G. OK, so now notice that I have my group G. It goes into out of Fn, and this acts on outer space. So what I can do is use this to build a copy of the Cayley graph in outer space. OK, so this gives me an equivariant embedding of the Cayley graph of G with respect to this basis S in Xn, where I send G to G times R, where let's call this is a base point. Let's call the base point the rows for the basis B. Right, so I have this nice basis that I picked. That defines the rows. Like, I just take that rows. That's with like equal edge lengths or whatever, with those elements as its label. That's a point in outer space. Now let me look at this orbit. And maybe here I'm using a left action before we did a right action. That's because I want like to act on the left on the Cayley graph. So I just flipped it around. And now how is this defined? This is defined by like do G inverse on the right, OK, as before. OK. So basically, what does this mean? I have this nice, this is just the orbit of this point. And I connect everything with the geodesic by just, for every basis, for everything in S, my basis for G, I take, so here's a rows R, and then here's SR, and I choose a geodesic like this, and then I propagate it equivariantly. OK, and then I have like a nice copy of my Cayley graph in the space. OK, and the upshot here is that for alpha in the free group and G in G, remember we care about the flaring condition, which is something about the lengths of conjugacy classes and with respect to the basis. Well, maybe I have to put an inverse here now. Well, that turns out to just equal the length of alpha at the point, at this corresponding point in outer space. Okay, if you like set everything up correctly. All right, so now these things we want to study are the lengths of elements at different points in outer space. Okay, everything's set up like that. And we want to use outer space now to establish the flaring condition for these guys. Okay? All right, we're almost done. Look at the last page. Here it is. Still have 3 minutes. Okay. Okay. So now remember that I have the following kind of picture. G sitting inside of the Cayley graph, which maps to xn, which maps to the free factor complex by this Lipschitz projection. And what I know is that this here is a QI embedding. So what does that tell me? That if I take any geodesic in G, I think of it as a path in the Cayley graph. When I map it down, I get a quasi-geodesic. That's exactly what it means for this to be a QI embedding. And we just had a nice theorem about paths in outer space that project to quasi-geodesics in the free factor complex. So we want to use that. Okay? So this says that any geodesic, these are the things that we cared about long ago in the flaring condition in the Cayley graph, projects to that this is a quasi-geodesic. I'm going to call it this way, in outer space, because, I mean, if this map is a QI embedding, the map into xn also has to be a QI embedding, because this map is Lipschitz. So anyway, so the embedding of the Cayley graph into xn is also a QI embedding. So this is now a quasi-geodesic, such that the projection to the free factor complex is also a quasi-geodesic. Okay, so that means it's strongly contracting for some uniform constant d from that theorem from before. Okay? All right. So now we can do the following thing. Okay, so let me draw a picture. So here I have G minus n rho, and I have my Cayley graph, whatever, and here's Gn of r, and in the middle I have G0 of r. And this is some quasi-geodesic that we now know is strongly contracting. So if I take a folding path between its two endpoints, which we know exists, or like you could rescale do a rescaling path and then a folding path. I could take a folding path, gamma, which I guess I already used gamma. Oh, yeah. Let me call it. This is the path gamma t. So I can take a folding path gamma t from the endpoints of this quasi-geodesic. And since we said before, these gadgets are strongly contracting, so they're more, so these have bounded Hausdorff distance. Okay, has the Hausdorff distance between this path and gamma is bounded. Okay, what does that mean? What do I care about? I care about the lengths of, at gi rho, I care about the lengths of the curves at those points. Right, I care, so this is the length at gi r of alpha. But over here, there's some other point, gamma ti, that's bounded distance. And if you're bounded distance, that means the lengths are basically the same. So this is basically the length at this point on my folding path. Okay, so I want to study these things. And now I've translated these conjugacy lengths to lengths along a folding path. Okay, because you're bounded Hausdorff distance. All right. Okay, so I guess here I'm labeling gamma t sub I is the point on the folding path that's close to gi r. Okay, because I know they have bounded Hausdorff distance. Okay, so what do we need to show is the flaring condition. All right. The flaring condition is that the length of alpha at 0, one of them is bigger so we want to know that, and this becomes instead lambda the length at gamma t0 of alpha versus the max of the lengths at the endpoints. So this is 0 versus the length at the other endpoint. Okay, so this is what I have to show, that this happens. And maybe without getting into too much of a detail, let me say use the structure of folding paths to prove this. And basically what I mean by that is you break the curve alpha, this curve alpha with its illegal turn structure coming from the core into legal and illegal parts. And what you show is that, we kind of talked about this before, if I have a legal bit, it grows when I go forward exponentially. And if I have illegal things, well, this is like kind of harder to show, they grow when you go backwards. Okay, so legal grows forward, and illegal grows backwards. And you prove that the legal bit grows at some definite exponential rate, the illegal bit grows at some definite exponential rate. So all you do is you look here at time 0, and you say, well, what is, my length is made up of illegal length and legal length. So there's some of both. Which one's bigger? If legal is bigger, I go forward. And then when I go forward, it will get bigger. If illegal was bigger, then I go backwards, and then the total length gets bigger. And then you get your flaring. Okay, so this implies the flaring. Okay, and that's how you prove the thing. So I'll stop there. Thanks.